Hello guys, I'm introducing to you a water tank with a length of 20 meters and the width of 3.7 meters. As you notice, it is divided into two compartments, 10 meters each. Now to have a better understanding of this water tank, let's get inside cross-section 1. As you observe, the initial thickness of the wall is 300 mm, but that's not the final size yet. Our final size will come from our analysis using ETABS and other parameters like crack width. Also, the height of the water is restricted to 3 meters with a minimum air gap of 300 mm. But if you try to look at my pressure or water pressure diagram, it's different. Here is 3 meters, but on my pressure diagram is 3.6 meters. Why is that so? Because I assume to be on the safe side, and at the same time to unify my solution, I assume a total height of 3.6 meters. Now if you want to do a exact solution or computation, it's up to you, but on my part, I just want to be simplified, and at the same time we're not just dealing with water but also earth pressure that is acting on the opposite side with a height of 3.6 meters. At surface, we have two main forces that are acting on the wall. One is the water, and second is the presence of the earth or the earth pressure, plus if there is a surcharge load on top of it, you may add on your solution. But I would like to introduce to you two cases or scenarios where the water tank wall may be subjected at critical point. The first case is just after the construction, meaning to say there is no backfill yet, because we're gonna test for the water leak. So there is no any soil on the perimeter or backfill on the perimeter of the water tank. Only water is available. So as you can see on my pressure diagram, it's only water. The second case is during maintenance, meaning to say the water tank is somehow being emptied. So without the presence of water, only the earth pressure plus the surcharge load is going to be assumed. Now for this problem, I have assumed a surcharge load of 12 kilopascal. You may find it too much, but for the purpose of computation, I have assumed 12 kilopascal. I would like also to highlight some important points here. The water table is just at the base of the water. Also, the angle of internal friction is 30 degrees, and the density of the soil is 18 kilonewton per cubic meter. Now, where are these data coming from? It will come from the soil report. Now at this point, I want you to focus on these two diagrams here, because later on we're going to be computing for the maximum pressure at the base for these two diagrams. For the first diagram, of course, it's a water pressure. It is represented by a triangular load or a uniformly increasing load. Again, for this case, only water is going to be considered for the analysis. For the second diagram, as you notice, it is represented by two shapes. One is triangular and the second one is rectangular. For the triangular load, that represents the earth pressure, while for the rectangular load, that represents the surcharge load. Again, for this case, only earth pressure and surcharge loads are going to be considered for the analysis. Now the question is, how are we going to compute for the maximum pressure at the base for both cases? So first, let's compute for the maximum pressure at the base of the first diagram. Of course, our formula is P equals gamma water, height of water. I hope you can still recall this formula from your hydraulics. Now, for the gamma water, of course, that's 9.81 kilonewton per cubic meter times the height is also given as 3.6 meter. Let's use our calculator. 9.81 times 3.6 equals, that's how much? 35.32 kilonewtons. So we will write here 35.32 kilopascal. This one will cancel out. So what remains is kilonewton per square meter, or 35.32 kilopascal. So this is the pressure at the base of, the first case, which is 35.32 kilopascal. For the second case, it's quite a bit tricky because we're going to be introducing a coefficient, which is the Rankine's coefficient, to solve for the pressure at the base given the soil pressure and the surcharge load. So we're going to be dealing first with the triangular load. The triangular load represents the soil pressure. It is given by the formula. Let us assume that this is P1 and this is P2. For P1, it is given by the formula. It's still the same as water pressure, gamma of soil times height of soil. Okay, but we have to multiply a coefficient here called Ka. What is Ka all about? This is a Rankine's coefficient for active pressure. And it is given by the formula 1 minus sine of the angle theta divided by 1 plus the sine of the angle theta. As we all know, the density or the angle of internal friction is 30 degrees, which means that we're going to be substituting it here, 1 less sine 30 degrees all over by 1 plus sine 30 degrees. Now using your calculator again, 1 less sine of 30 degrees divided by 1 plus sine of 30 degrees. That's a total of, that gives 1/3. 1/3. Meaning to say that P1 now is equals to 1/3 of the density of soil. Density of soil is already given, correct? It's 18 kilonewton per cubic meter. It's here, 18 kilonewton per cubic meter. So we're gonna substitute from the formula 18 kilonewton per cubic meter multiplied by the height of the soil, which is 3.6 meter. Let's use our calculator. So it's 1/3 times 18 kilonewton times 3.6 meter. That's a total of 21.6. So this is 21.6 kilopascal. That's only for P1. What about P2? For P2, it is given by the formula KO multiplied by QA. Now, what does this KO all about? KO is a Rankine's coefficient for a condition where it is at rest. Meaning to say, like for example, for surcharge load, it is at rest. So we're going to be using KO. And QA represents the surcharge load. So direct substitution, KO is, we don't know yet the value of KO, but we can compute. KO is represented by the formula 1 less sine of theta. 1 less sine of 30 degrees. Let's use our calculator. 1 less sine of 30 degrees equals 1/2. So it's 1/2. 1/2. P2 equals KO 1/2 of 12 kilopascal. That's a total of 6 kilopascal. Now, that's just P2. What we are after is the total pressure at the base, which is the sum of P1 and P2. P now equals P1, which is 21.6 kilopascal. Don't forget the units, plus 6 kilopascal, which is the P2. That's a total of, using our calculator, where is it? So that's 21.6 plus 6 equals 27.6. Where's the pen? 27.6 kilopascal. So did you notice, if we try to compare pressure 1 and pressure 2, for the first case, you might guess that this is smaller because it's only represented by one shape, which is triangular. While for the second case, it is represented by two shapes, which is triangular and rectangular. You might guess that this is bigger as compared for the first case, but as you can see, the pressure at the base for the second case is 27.6 as compared with the first case of 35.32. So that's all for the pressure at the base of these two diagrams. Now, we are going to consider these pressures in our models using the ETABS.